Great, welcome everyone. I'm disappointed you missed our pre-thesis defense banter, but now we started the official recording, and I have to say, I think I'm just as excited as I would be for an in-person defense. You know, you always get really excited and proud when a student defends their thesis, and the fact that Cole is managing to finish up and do this thesis defense despite all the challenges we're facing right now makes me even prouder and more excited for this thesis defense. So I'm Allison Okamura. Many of you know me already, but for those I haven't met yet, I'm Cole Simpson's PhD advisor, and excited to introduce him for this online thesis defense. Let me start by, for people who are not familiar with the process, letting you know how this works. So we have a public thesis defense with Q&A that lasts for about usually a total of an hour. Maybe those of you in the audience would like to grill him for slightly longer than that, that would be okay. And then we switch to a private session. And normally in person, this requires an awkward shooing people out of the room. But in this case, for the private session, we'll actually just be closing this public Zoom meeting. And then there'll be a separate Zoom meeting for Cole and the members to do Q&A for a while. And I always, for those of you who are going to be waiting for Cole to emerge from that private session, as I always tell my students, the private session may go long, it may go short. That time doesn't necessarily have to do with how well or poorly a student is doing. It just pretty much has to do with how chatty the committee members feel. So I'm sure Cole will alert everyone when he emerges from the closed session. Before I hand the floor over to Cole, I would like to do a little bit of an introduction. So I'm going to briefly share my screen. Another nice thing about the online thesis defense is I don't have to awkwardly plug in my computer and remove Cole's computer from the screen. In this case, I'm just taking over. Hopefully everyone can see. I'm just showing a slide to welcome everyone to Cole's thesis defense. And I wanted to mention that Cole came into my lab with just an incredible font of knowledge in things related to human motor control and robotics and human machine systems through his undergraduate work at Georgia Tech, as well as his Fulbright scholarship to study for his master's degree at EPFL. He came in knowing quite a bit more than I did about human motor control. And in the process, and I'm sure many other people from my lab, as well as other collaborators, have learned a lot from him. But we're very grateful that he decided to continue his education by coming to Stanford as a National Science Foundation Fellow. And in that process, exploring more the connection between device design and human motor control. And although I think none of us really anticipated exactly where the thesis would go, and you'll learn about this soon, I do think it's the perfect marriage of Cole's interest in neuroscience and the kind of design, I guess, attitude that we have at Stanford in terms of building and prototyping and doing it some more, and all the Cole especially doing excellent science in the process. So as a student, Cole is not super talkative to me about you know, his life and the things that he likes to do, but I've gathered a few things in terms of like what he likes. You can see his surfboard. I assume that's your surfboard sitting behind you. Is that right, Cole? You're muted. So
this is one of the surfboards, yes.
One of the surfboards, okay. Doesn't surprise me to hear there are multiple surfboards. I know we bonded a little bit over the fact that he likes to run marathons. And I hope you're getting some outdoor time, Cole, even during the shelter in place. He likes making figures. He, with his partner in crime, Sean Sketch, have tutored many students in our lab in making beautiful figures for papers and presentations. And it's another type of collaboration I have Cole to thank for. And he also enjoys writing, and writing well, as one of his thesis committee members commented on recently. And he enjoys really helping other students in the lab. I could not even possibly count the number of times students said, well, I talked about this with Cole, sometimes for hours. Cole is always willing to brainstorm and is very intellectually curious and scientifically minded. And also he likes Switzerland. I have to say, I was kind of wanted to make a list of dislikes as well. But he seems to pretty much like everything. I have not ever heard Cole really complain about anything, and in that sense, he's been an amazingly pleasant student to work with. I'm sure you have something you dislike, Cole, but you've never really complained to me about anything. I'll note that in the process of both his earlier research as a master's student, maybe even some of this is undergraduate work, as well as the work he's done since he's come to Stanford, Cole has really put out an impressive set of papers. Out of all of these, only a couple are relevant to the PhD defense, but even those that are not listed in his PhD or described in his PhD are all very important works that anyone would be proud of to include in their PhD, but Cole can only cover so many topics in one thesis. So I'll just end by noting that Cole's been around the lab for a while. This is maybe not from the very beginning of when he started in the lab, but for some reason it was the clearest picture I could find. Plus it has Susha with his free hugs shirt. So I had to include this one. Cole has been an amazing part of the growing group of my lab and supporting other students. And then since these early days, of course, things have changed a lot. So here's a recent lab meeting from 2020 with Cole, very similar to his current position with the surfboard behind him, participating in a recent online lab meeting. So even the lab photo genre has changed in current times. But I'm so glad that everyone could come together for this PhD defense, especially glad that that Cole's parents are here to join us, and also that so many of you could tune in remotely to participate in this very important event. And with that, Cole, thank you for everything that you've done in our lab, and I will pass it on to you. Stop sharing my screen so that you can take over and defend your thesis.
Great. Thanks very much, Allison. I will go ahead and add something to that list of dislikes, which is paperwork. Unfortunately, there is some considerable amount of that during the PhD, but we survived. Okay, so I'm just trying to set things up here. So hopefully you can all see now a title slide with the title of my dissertation, which is Wearable Devices for Physical Assistance, Enhancing Capabilities After Stroke and in Running. And I think one thing that Allison didn't mention is that this is our first lab defense on Zoom. And so we're trying to make a couple of adaptations to suit this new venue or new format. One thing that I've done here is I've reserved a little square in the top right hand of the screen, which is I'm calling the safe place for Cole's face. So if you put the little video of me there, it won't cover up too much of the content that's going on here. And so right quick, I want to just give it a quick outline of what we're going to talk about today. First, there's going to be an introduction, and then we'll talk about some upper extremity devices that we designed for a stroke application. Then we'll move to some lower extremity devices for a running application and end up in a conclusion. And generally, this is kind of organized as most complex to least complex. Hopefully that'll make sense in a minute. So I'm going to start out by pointing out that we humans develop tools to help us accomplish physical tasks. In many cases, these tools actually even reshape the environment that we live in. So one key example being stairs that are not common in nature, but are very commonplace in our environment to help us move up and down slopes and to different floors. And we have other tools to help people with motor impairments. So one easy example is a wheelchair to help people with difficulties walking to move around. However, because we've designed our environment around healthy people, sometimes our assistive devices, like a wheelchair, is not optimal for getting around in the environment we've designed for ourselves. So wheelchairs are kind of famously incompatible with stairs. So the way that we propose to overcome this is by making an assistive device that's more in the form factor of a human with no motor impairments. And so these devices are generally considered to be exoskeletal robots. So this is a robot that is worn by a user that applies forces directly to the person to help move them around. And today there's kind of a widening plethora of examples of exoskeletal robots that do everything from help people to walk and run faster and more efficiently, to lift heavy objects with greater endurance, and to assist people who have had issues with moving their own body around to move, and to complete therapies. But most of these exoskeletal robots are very expensive. So I think the cheapest one of these commercial devices I found in my survey was this Rewalk Personal 6.0. It's $60,000 to $80,000, depending on how you spec it out. And even some of them go way on up into the $350,000 range. And so as such, most people cannot afford their own exoskeletal robot to help them move around or help them accomplish their tasks. And this cost barrier really limits our access to these assistive devices. And this can really limit the outcomes of these devices. So just as an example, just as a case study, some of the largest studies that have been performed of robot-aided stroke therapy have tested 20 to 30 hours of robot-aided therapy in stroke survivors. And a part of the reason is because the hospital itself, where these studies are performed, can only afford 1 or 2 examples of these robots. And if you have 20 or 30, 40 people that need to use it, then you have a very tight schedule and people have very limited access to it. And so as a result, we see some improvements in stroke outcomes as a result of this robot-aided therapy. But according to studies in animal models, much higher doses of thousands of hours might drastically improve the outcomes that we see. But we can't perform these studies unless we have more accessible devices. So one of the ways that we try to make exoskeletal robots more accessible is by removing components. Additional components add cost and complexity, which makes the engineering harder, which drives up the whole cost of the system. So one way to handle this cost problem has been championed by the Harvard Biodesign Lab, which is they're calling exosuits, where basically they remove the skeleton component of the exoskeleton. So rather than using this, metal linkages and carbon fiber linkages as a transmission from motors to human, they just attach the motors directly to the human and have the motor move the human around for them. And so these are comparatively new technology, so there are not very many commercial examples yet. But one of the ones that is available is the Rewalk Restore, which is about $30,000 US, which is about half the price of their comparable exoskeletal robot. And I do want to note that controlling these exosuits is still a difficult challenge. So it's really difficult with a limited set of measurements to figure out what the human operator is trying to do so that the robot can provide the needed assistance. So another approach at simplifying exoskeletal robots is to remove not only the skeleton, or rather leave the skeleton in, but to remove the brain. and also remove the muscles, the motors. And so what we do here is use energy stored in springs and maybe some other pneumatic reservoirs to help move the body around. And these are a much cheaper, more accessible version of the exoskeletal robot, with commercial examples costing $5,000 to $8,000. So still, this is kind of getting into the realm where people can maybe afford one for at-home use if they really, really want it. But unless insurance steps in to pay part of the bill, it's unlikely that these would achieve widespread adoptance. So our mission statement here today is to make inexpensive devices that aid in human movement. And with that, I want to move on to our upper extremity stroke application. And so strokes are the leading cause of adult disability. A stroke occurs when a lack of blood supply to part of the brain kills off the tissue there. And as a result, we can have a whole range of motor and sensory impairments. And these occur particularly when the part of the brain that controls, for instance, the arm movement dies during a stroke. Now, luckily, the human brain is a kind of a flexible organism, and as a part of stroke recovery, will attempt to rewire itself to try to compensate for the missing portion of the brain now. Unfortunately, the healthy portion of the brain is not frequently able to control individual muscles in the same way that the unaffected brain is. So rather we end up with synergy, or what's called the flexor synergy, is a common manifestation of this. So the flexor synergy is one example we're seeing here on the right, is the shoulder abductor muscles become coupled with elbow flexor muscles and wrist flexor muscles, so that whenever you're trying to say, if I'm trying to reach to a glass of water positioned over here, I lift the arm up, and when those shoulder muscles start activating, the biceps or the elbow flexor muscles and wrist flexor muscles also activate and contract the arm out together, and I'm not able to overcome those muscles to reach out to my glass of water. We do have this empirical example, though, of if we provide some support to offload the effort of these shoulder abductor muscles, typically done with an exoskeletal robot, the activation of those shoulder abductor muscles is reduced, which allows the flexor muscles of the elbow and wrist to relax a little bit, and they're able to reach out a little bit further. And so in the studies where this is examined, the measurement that we're primarily looking at is the reachable workspace area. So if you're looking top down on someone trying to reach to the glass of water, or you really even just draw the largest possible circle that they can reach on a tabletop, we define the shape of that as the reachable workspace boundary, and we compute the area of that. And that reachable workspace area increases with shoulder abduction support. So the one problem is that these studies primarily rely on these big, expensive exoskeletal robots that can cost $250,000, $350,000. And so I thought it would be a really good idea to have one of these devices that is, one, way less expensive, and two, you can get up and move around with. So for instance, rather than being limited to performing your therapy in the clinic, you can take it with you, and everything that you do, whether it be getting groceries at the grocery store or doing the dishes, could be an opportunity for therapy. And so I took this idea to Allison, and she said, great, talk to Elliot. And so lesson one with working with Elliot is that anything can be a robot, whether that's popsicle sticks and rubber bands to the full-on aluminum, titanium, carbon fiber constructions we're used to seeing. So this was our first attempt at providing shoulder abduction support with a low-cost device. What we did was we took inelastic nylon cables. Basically, these are backpack straps. And we wrap them over the shoulder so that when we lift up on the strap, it lifts the arm. However, we need something to attach the other end to. And rather than grabbing onto the upper arm, which is kind of squishy and could be really uncomfortable to squeeze it hard enough to get a good grip, we went all the way down to a glove attached to the hand. And so we pull on that glove, which provides that reaction force that we need to lift the arm. But that also means that we need to intelligently route the cables across the arm such that every time we pull it, we don't just end up with an even worse flexor synergy. So we route the cables such that they cross the elbow and the wrist at a 0 moment arm configuration, so that when we pull, there is a compressive force on that joint, but there's no rotation of it. And with this setup, we were able to fully support the weight of the arm with our cable while still allowing motion of the elbow and the wrist. But it was very uncomfortable. And so, in fact, too uncomfortable that it was more uncomfortable than it looks here. So we iterated a couple more times and figured out that maybe a much simpler way to handle this problem is to essentially put a balloon in your armpit. And so that's what we did here. We attached the balloon underneath the arm, the upper arm, so that the elbow remains free to rotate. And as we inflate and deflate the balloon, the shoulder abduction angle goes up and down. And the balloon is sewn to the side of the torso with a single seam that allows it to rotate about the torso, allowing for shoulder flexion. So this is great. What we really wanted it to do, again, was to support stroke survivors in one, abducting the arm, but two is increasing that reachable workspace in the horizontal plane, which is interesting to note that that is not the direction we're supporting. So we did recruit one stroke survivor who came in, and we performed this maximum reachable workspace area experiment with our stroke survivor in both the unsupported case and with our exomuscle support. And we found a huge increase in workspace area with exomuscle support. However, one of the primary limitations of this device was that we coupled the air pressure in the balloon with that shoulder abduction angle. And so this is great at high angles and high pressures, but at low pressures and low angles, we end up with a really mushy support. It's very easy to just kind of fall off the column of support and get trapped on the side. So what we really wanted to do here was somehow decouple that shoulder abduction angle with the air pressure provided in the balloon. Luckily, Zach Hammond next door was working on something called that they're calling a pneumatic reel actuator. And so this is a compliant actuator that's capable of really high extension ratios and can even carry a payload. These are little masses that it's lifting up and down, and it's robust to perturbations in the environment. And so this actuator consists of a little thin-walled tubing, which can be inflated with pressurized air. That tubing is then wrapped around an axle, which is the reel part of the pneumatic reel actuator, and that's housed in this base station. And so as the tubing is wrapped around that axle, a spring or a motor can be controlled to spool and unspool that tubing to change the length of the actuator. So this seems pretty ideal for our purposes. So we made kind of an industrial sized version of these, one of these pneumatic reel actuators. So we moved that base station, attached it at the hip. So this is the heavy portion of the actuator. We want to put it as close to the body as possible. So we attached that to the hip, and we attached the light end of the tubing underneath the arm in the same way as our previous bladder. Then we inflate that bladder with an external air source, and we can change the shoulder abduction height by spooling and unspooling that bladder around the reel. And this way we can keep the air pressure constant and the stiffness of that support constant while we change the height of the support. And just for a comparison, just to see how good our device is, we constructed what we're calling a ceiling support as a positive control. So this is a commonly used technique for providing a similar type of support for people to do this type of exercise at low cost. And you might think, okay, well, this seems to be a very low cost solution to this problem. Why not just do that instead? Well, the answer is that we also wanted our device to be wearable. So with the ceiling support, you are tied to the ceiling, so you can't get up and go use it at the grocery store. Whereas our wearable device, if you're able to onboard the power supply, you can just get up and walk off and continue to receive the support. So before testing our device in a vulnerable stroke population, we want to make sure that everything is going as we expected in healthy participants. And so there we asked two basic questions. One, does it help? And two, does it get in the way? Does it interfere with normal motion? So we recruited 4 healthy participants. And first, to measure does it help, we were primarily interested there in that shoulder abduction support. So we measured the activity of the shoulder abductor muscles, which are the deltoid muscles. And we did that in our 3 different support conditions, 1 with no support, 2 with exomuscle support, and 3 with ceiling support. And we did this in an isometric task where the arm wasn't moving, and in a dynamic task where we were performing some reaching tasks. And what we saw is the average muscle activity goes down in both supported conditions relative to the unsupported condition. So both the exomuscle and ceiling support reduce the activity of the shoulder abductor muscles by the same amount relative to the unassisted condition. So we conclude, yes, we are providing the assistance that we hoped to provide. So our second question was, does it get in the way? And so there we wanted to make sure that the other joints are still able to perform whatever they want to do unimpeded. So we measured the elbow range of motion and shoulder flexion range of motion with all 3 support conditions, and found that there's no change across any of the conditions. And so we do conclude that at this point, our device was worn by many healthy participants without any emergencies. It provided the help that we designed it to do, and it didn't interfere with other joints going about their business. So at this point we say, all lights are green, let's move to stroke survivors. So we recruited 6 stroke survivors. They were all chronic stroke survivors, so they were more than 6 months post-stroke. And this is important because in that first 6 months after a stroke, a lot of things are changing due to the recovery process. And so we just want to make sure that everything's settled down there. All the stroke survivors that we recruited had upper extremity weakness, as opposed to some other type of difficulty that we can't help them with our device. They must have full passive range of motion, meaning that their arm can be lifted to shoulder height and moved around without any pain. We don't want to hurt anyone. And we asked basic accommodations questions just to make sure that they could make it to the lab and sit in the chair for the amount of time we needed. It didn't have any other health problems that we would have to worry about. And so in stroke survivors, we again asked 2 basic questions. 1, does it provide the help we designed it to provide? And 2, why are we seeing the results that we're seeing? So the support we designed it to provide, this was again back to our reachable workspace area that we tested with our previous device. So each of our 6 stroke survivors performed a protocol in which we measured the whole reachable workspace with 3 support conditions: unassisted, exomuscle support, and ceiling support. As you can see from our graph here, there is a lot of difference between participants, but it's a little bit hard to make comparisons with this type of a graph. So what I did here is I plotted on the vertical axis the workspace change due to exomuscle support. And so here, anything above the dashed line is an increase in reachable workspace area relative to the unassisted case. Anything below that dashed line is a decrease in reachable workspace area relative to unassisted. Now, on the x-axis, I plotted the unassisted reachable workspace area. So on the left-hand side, you see people with that had very small reachable workspace area in the unassisted case. And on the right side, you see people with a much larger reachable workspace area. And so what we do see here is that 4 of our 6 participants did have an increase in reachable workspace area of 180 square centimeters on average, where 2 did not. The interesting thing to note here, though, is that the 4 that did receive or that did increase in reachable workspace area were the people that had the smallest unassisted reachable workspace area. So these were the people that needed the most support or had the most to gain. Whereas the people on the right end of the plot, maybe they were more close to a healthy reachable workspace area, and our device, though it didn't get in the way of our healthy users, maybe impeded their motion a little bit. The other thing that we note is that our ceiling support vastly outperformed our exomuscle support on this reachable workspace area metric. And this kind of leads us to our second lesson of the day, which is that you have to test your device in the target population. So even though these 2 devices looked exactly the same in our healthy subjects, and most of the studies that test similar devices kind of stop there and mark it as a success, the performance of the 2 devices is very different in the stroke population. And so even though these healthy measurements can be indicative that we will receive some benefit in the stroke population, it doesn't tell us much about how much of a benefit. So this leads us to our question of, why do we see what we're seeing here? And here, our hypothesis was that we are increasing the reachable workspace area by offloading that flexor synergy that becomes erroneously activated after a stroke. And so what happens there is our flexor synergy causes our elbow flexor muscles to activate whenever we lift the arm, which limits the elbow range of motion, which cause our constricted workspace. And so what we do so we wanted to compare our reachable workspace area with our elbow range of motion and with our shoulder range of motion to see if it's related to either of those. And we do see on the left-hand side a strong correlation between reachable workspace area and elbow range of motion, which does support our flexor synergy hypothesis, where on the right-hand side, we see no real strong correlation between our reachable workspace area and shoulder range of motion, which is as we would predict from our flexor synergy hypothesis. So then we want to measure or compare our elbow range of motion and reachable workspace area with measures of flexor synergy activation. And we do see that our elbow range of motion on the left is weakly correlated with the flexor synergy activation, and our workspace area is also weakly correlated with flexor synergy activation on the right. Now I do want to note that these are kind of weak correlations, but they do go in the direction that we expect them to based off our hypothesis, and that our flexor synergy measure here is an indirect and noisy measure of the thing that we're actually trying to measure, and that not all of our stroke survivors might have actually had an erroneous flexor synergy activation. So we do count this as a success in our book, that our hypothesis that we are increasing reachable workspace area by offloading flexor synergy is supported by our data. So in this section, we have created a new wearable, inexpensive type of exosuit actuator, and we have demonstrated that it increases reachable workspace area in some stroke survivors, even in the unassisted directions. We also demonstrate that 2 devices, which look exactly the same if you only look at healthy users, look very different in stroke survivors. Now, there is a little bit of maybe a dirty secret in this work so far, which is that we've only really made the exosuit actuator. It's not a complete exoskeleton or exosuit. We don't have a controller, and we're relying on off-board pressurized air to provide the power for our device. And so what we really wanted to do, again, is move towards something that is fully wearable while still being inexpensive and totally portable. So to that end, we made a new passive exoskeleton rather than an exosuit, passive exoskeleton, for shoulder abduction support. And to do this, we made an aluminum frame with a pin joint that aligns with the shoulder along that shoulder abduction axis. And it is powered with pre-stretched elastic bands that are connected at the bottom end of that frame and at the proximal end of the arm linkage. So that provides a near constant force so that we get an arm lifting force that varies with position due to a changing moment arm. We also have a tensioner that just helps maintain alignment and a custom 3D printed arm cup to mount it to the arm. So I do want to note that if we have an arm that, if we model our arm as a pendulum and we want to look at the support that we want to provide as a function of shoulder abduction angle, we would want a sinusoidal support. And this is just a graph to show that a sine function does a great job of explaining the data of our device. So it does provide the torque profile that we would want it to provide. And apologies, I think that this video looks fine on my screen, but I think that there's some issues with it over Zoom. But I just wanted to show that we can take this device outside in the wild. It's totally wearable, totally portable. It is compatible with backpacks and jackets that can mostly conceal it. And that it can provide that supportive torque that we designed it to provide across a range of stretches and activities. So before moving to testing with a stroke population, we want to again make sure that this device is safe to use in healthy participants and that it does what we wanted it to do. So we go back to our same two questions from before. One, does it help? And two, does it get in the way? So this time we recruited 6 healthy participants, and we again measured in a stationary isometric task and in moving dynamic tasks that the shoulder abductor muscle activation is decreased. And in both cases, even though we didn't tune the support precisely for each subject, we just kind of set it to a certain level, but we still decreased the activation on average by 50 to 60%, which was statistically significant. So our second question was, does it get in the way? And so here we measure the range of motion of elbow, the shoulder flexion, shoulder abduction, and shoulder rotation. And in every case, we found that it did not significantly change the range of motion. So we conclude our device provides the assistance that we wanted it to. It is safe to use in a healthy population. It doesn't get in the way of any of the other joints. So at this point, we're ready to move to our stroke subjects. Unfortunately, this is where we run into the current situation where all studies with human subjects and especially vulnerable populations have been placed on hold. And it's unclear when we'll be able to do these, but we have everything set up and prepared for when we get the green light. And so we're hopeful that we will be able to move to stroke participants at some point. So in this chapter, we designed a new, low-cost, go-anywhere passive exoskeleton and demonstrated that it does exactly what we wanted it to in healthy participants with no unforeseen side effects. So at this point, I want to, we've been going down a track of trying to make our devices more and more simple. So we've gone from an exosuit actuator where we need a full power source and controller, and have removed our controller and power source and ended up with a simple spring and frame device in the last chapter. But this led us to ask the question, what is the simplest device that we could make that demonstrably aids in human movement? And for this, we want to move to our running application. And so why running? Well, the reason for running is because it's inefficient. So on this graph, we see the energy required to move a given distance on the y-axis, and we see the body mass of different animals on the x-axis, and we see different modes of locomotion in which running consumes more energy to move than flying or swimming. It also requires more energy than walking, but that's not shown here. Now, this this inefficiency means that there's opportunity for us to provide some sort of improvement. And I think there's an interesting question of, what do we mean by running is inefficient? Running is running, and it takes the energy it takes to run. But what we mean from an engineering standpoint is we're looking at the energy that we use, the energy we consume, compared to the work that we get out of the system. And so in running, the only external force that we're overcoming in running is aerodynamic drag. And early studies that try to estimate how much energy actually goes into overcoming aerodynamic drag place it as less than 10% of the energy used in running goes into overcoming that aerodynamic drag. So you could kind of consider all the rest of the energy, 90+% of the energy, to be wasted. And so if so much of the energy is wasted, where is it going? So here's a pie graph that shows in blue the energy that's used to the useful energy that goes into overcoming air drag. And in shades of red, we see the energy that goes into various other processes. So 11% of the energy goes into keeping us alive, basically, and keeping us cool while we're running. But most of the energy goes into the stance phase of running. This is basically jumping up and down and maintaining balance. And since stance phase consumes most of the energy that's wasted in running, that's where most people designing assistive devices to aid in running have focused their efforts. And so we've had a lot of creative approaches that have had varying levels of success in making running more efficient. My personal favorite is running with a jetpack, but probably the most widely used is Nike's new Vaporfly shoes, which improve running by 4%. However, we, in an attempt to buck the trend, we noticed that a not inconsiderable amount of energy is lost during leg swing. So rather than the energy used to jump up and down, this is the energy that's used to swing the legs back and forth during running. And we did, after a little bit of digging, noted that a lot of animals, in fact, have tissue that they've evolved that helps them to swing their legs, or equivalent tissues of wings and tails, to facilitate locomotion. So in birds and mammals, frequently tendons and muscle tissue can act as a passive spring that helps them to swing the leg or the wing more efficiently. In fishes and sharks, that elastic tissue is collagen, which is actually embedded in the skin, which acts as a normalizing spring. And in insects, there's a special tissue called resilin, which acts as a spring. So the way that this works is that if you imagine a leg or a wing or a tail as a pendulum, if you were to drop that pendulum, it'll oscillate at a natural frequency. Now, it is possible to swing that pendulum faster, but that requires us to put in external energy. So in animals, this comes from the muscles. If you add a spring in parallel with the muscles, however, when the pendulum is slowing down in order to stop and redirect itself, the spring stores some energy that it then returns, that accelerates the pendulum back the other way. And so in this way, the total moment required to drive the pendulum at a given frequency is offset by the moments provided by the spring. So this got us to thinking, what if we were able to take a spring and attach it on the outside of a human runner in a fashion that would help oscillate the leg? Would that improve running economy? And so we developed such a spring. In this case, we used latex rubber tubing, or essentially we made a rubber band, and we attached it to the shoe because this allowed us to have very low forces because it's very far from the hip. And when trying to consider where to attach the other end of the rubber band, we realized that the legs in running are basically going out of phase of each other. So they're both braking at the same time, more or less, and accelerating back towards each other at the same time. And so we could essentially attach that spring to both shoes. And that would provide that moment that we're looking for to help swing the pendulum. So to verify if our spring improves running economy, we developed an experiment that was conducted over 2 days and recruited 12 healthy participants. And in our experiment, each participant completed 10-minute runs that were performed either in the natural case where there was no, we call it an exotendon, no exotendon, or in the exotendon case with a 5-minute rest in between. And they're randomly assigned to start with either the exotendon case or the natural case, and then proceed in an alternating fashion. So I do want to note, just for future comparisons, we consider a trial to be the back-to-back comparison of a natural and exotendon run. So the percent difference between the exotendon and the natural run. So over the course of the 2 days, participants completed 4 trials, 2 per day. So we did find that, in fact, our rubber band does improve human running economy. At the end of our first trial, here we see on day 1, there was no real change in human running economy, but over the course of the 2-day experiments, subjects gradually learned how to run with the rubber band, and once they figured it out, we had, on average, a 6.4 reduction in human running economy due to our rubber band. And we do note that every single one of the participants did receive benefit from the rubber band. However, while we were doing this, we noticed some odd adaptations. One in particular we kind of fixated on, which was that every single one of the participants adapted to shorter and faster stride frequency. So when running at a given speed on a treadmill, where we fix the speed, you can take long, slow steps, or you can take short, fast steps in order to run a given speed. And for some reason, all of our participants adapted to a faster stride frequency. So we thought that this must be important in some way to the functioning of our device. So as I said, we wanted to kind of look under the hood here and look at why they might be adapting to this higher stride frequency. So as I said, you can choose your stride frequency to be faster or slower to run a given speed. And the reason that we adapt to the stride frequency that we pick is that it's more or less the most efficient stride frequency. So if we were to take slower, longer strides, we would require more energy in the stance phase of running to jump up and down, even though we require less energy to swing the leg back and forth. If you were to adapt to a higher stride frequency, where we're taking shorter, faster strides, even though the stance energy required to jump up and down goes down, the energy required to swing the leg back and forth goes up. So we make the observation that our rubber band does not affect the stance leg. So with the rubber band attached to the shoe, when the shoe is on the ground, assuming that it's not sliding relative to the ground, which we did not observe in our experiments, the forces applied by the rubber band are reacted directly by the ground, by friction with the ground. And so that stance leg is not affected by the rubber band. It's only the swing leg, the leg that's in the air, that is affected by the rubber band. And so our hypothesis is that the exotendon shifts the energy required to swing the leg to a higher stride frequency. Now, if you add this with the unchanged stance energy curve, you get a new total energy curve that is shifted down and to the right. And this kind of meshes with our observations that all our 12 participants, 1, adapted to a higher stride frequency, and 2, the total energy used was lower. So an interesting thing that we would not have predicted without this model is that even though our rubber band is not affecting the stance leg, we would predict from our model that the runners who have adapted to running with the rubber band are in fact using less energy in stance. And again, this is pretty counterintuitive for us, but the model predicts it, so we thought we would investigate. So in a subset of our 12 participants, we had them come back for a third day of experiments, where we moved them to a force measuring treadmill and measured motion capture, in addition to the gases that they're breathing in and out, and also what the muscles are doing. And compare, again, running with the rubber band to running without the rubber band. So through some kind of complicated math that Scott Delp luckily did for us in the 90s, we were able to compute the moment generated by the human about the hip and about the knee. So this is moment and torque are kind of similar terms for someone that recognizes one but not the other. And so in dark red, we have running without the rubber band. In lighter red, we have running with the rubber band. And in blue, we have the moment applied by the rubber band at the hip and the knee. And so the way that these graphs are set up, on the left-hand side, we have the time in which the foot hits the ground. On the dashed lines, we have the time when the foot lifts off the ground. And at the right end of the graph, we have when the foot strikes the ground again. And so here again, we're looking at stance phase and swing phase, where stance phase is the part of the graph to the left of the dashed lines, and swing phase is the area to the right of the dashed lines. And so these lines look pretty, but they're a little bit hard to make objective comparisons. So we computed the average absolute value of these curves, both in the swing phase to the right of those dashed lines, which are on the right here, the far right, and to the left-hand side of those dashed lines in the stance phase, which are on the left-hand side of our new graphs here. So as we would have expected, the hip and knee moments required to swing the legs back and forth both go down. They both decrease. And interestingly, as our model predicted, but as was counterintuitive for us, the moments at the hip and knee both go down during stance phase as well. So it does seem as though we are not only aiding in swinging the legs, but also in the stance phase. And so I do want to note that the moment or torque is not exactly the same thing as metabolic energy, though there are a number of relationships between the two, so they're highly correlated. Happy to discuss this for anyone that wants to know more. For now, it's a reasonable proxy. So in this section, we've created a new device that improves running economy by 6.5%. Now, this is the 6.5% number is interesting because it's outperforming a number of powered devices in running, full exoskeleton powered devices, and also the Nike Vaporfly shoe, which costs $250 and improves running economy by 4%, compared with our 6.5% out of $1 worth of latex rubber. We also provide a powerful theoretical biomechanical framework that both explains the mechanism underlying our adaptations here and makes predictions about things that we wouldn't have thought, which suggests that that is a very good model. And this might have strong implications for legged robotics and future assistive devices. So we were lucky in getting this work featured on the cover of Journal of Experimental Biology. And I do also want to note that there is something known as the Ig Nobel Prize, which honors achievements that make people laugh and then think. And this is my shameless plug that if you think that tying your legs together actually makes running easier, makes you laugh and then think, please write to them and nominate us. It would be pretty neat to see something come out of that. So now I'd like to move into the conclusions of the thesis. So we did make a number of inexpensive devices that aided demonstrably with human movement. We did this by though the classical approach to designing an exoskeletal robot is kind of to design a very high fidelity, very capable robot, and then figure out a way to wrap it around a human. What we did here, instead of that, is to look at very targeted neuromechanical insights, use these to inform our design, where we target very specific portions of the task needed to be accomplished. So swinging the leg or supporting the shoulder in order to do planar movements of the arm. And in some cases, this targeted design gave us new neuromechanical insights, which might inform future designs. So we end up with a little bit of a chicken and egg situation here. However, we also note that there's a chicken and egg problem with exoskeletal devices, which is that we don't know and kind of cannot yet know the long-term effects of external assistance. So I mentioned at the beginning that the biggest studies of exoskeletal robot aided stroke therapy have tested 20 to 30 hours of assistance. And that's due to accessibility issues. If we're really to know what will happen, what will be the effects of hundreds or thousands of hours of exoskeleton assistance, we need devices that are more accessible, and therefore we can provide assistance for that amount of time to more people. And you can imagine that someone who uses an exoskeletal device for their career, the calculation on a time spent in a career wearing an exoskeletal device, assuming you do that job your entire career, would be 80,000 hours. So our 20 to 30 hour validations are maybe not predictive of what we might see over much larger timescales. I also want to note that our passive devices have worked well for now. These are currently proving to be the most accessible devices, and due to their simplicity and transparency of operation, frequently provide as good a performance as more complicated devices. However, they're very limited in scope. So for instance, our rubber band used for running, if you decide you're stopped running and now you want to switch to walking, you need to take off the rubber band. That is no longer helping you to do the task. And even if you want to run at a different speed, the rubber band that we tested may not be optimal for every speed. So what we might need in the future are hybrid devices that use a small amount of power to switch between passive devices or engage or disengage our passive device. Ultimately, however, our passive devices are pretty limited. So just because we put a rubber band on someone does not mean that they can run. And just because we put our passive exoskeleton on a stroke survivor does not mean they have perfect control of their arm now. For some applications, like a spinal cord injury, the only tool that might be good enough is a full-on powered exoskeletal robot. And so that will, of course, necessitate continued development of those exoskeletal robots, their controls, the power sources, the sensors, and actuators. It's a full stack problem. And with that, I'd like to move into most people's favorite portion of the defense, which is the acknowledgements. So I really want to thank Allison for having me at Stanford, giving me the opportunity to really explore a wide range of different areas in research, and by giving me all the support that we need to do this and do a good job. However, a side effect of that freedom is that sometimes we'll wander a little bit far from the things that we both know, and we've been lucky at Stanford to have excellent collaborators with Elliot, Steve, Scott, and Martin, who are always happy to step in, provide a little bit of extra support and assistance and the resources. And Michael, too, thanks for agreeing to chair my committee, and look forward to having good discussions about the thesis. I do want to give a special shout out to Kara and Sean, who have been the people kind of in the trenches with me day in and day out for the last 5 years. and they've had to put up with a lot of abuses from me. And thanks for bearing with me, guys. Lesson 3, which is the same picture that Allison presented earlier, I noticed. Ask for help. This is one of the great things about being a member of such a large lab like the CHIRM lab, is that whatever problem you have, someone knows the answer. And everyone's very generous here and are willing to share their advice and expertise and their time. And as Allison mentioned, the CHIRM lab has changed quite a bit over the years. Both the people, some of the faces have changed, also the scenery has changed. But thanks to everyone there. Also, thank you to the Stanford Nimble and Scott for hosting me in both the Human Performance Lab and at numerous lab meetings, and for one-on-one support and advising. And also thanks to the Stanford Biomechatronics Lab. This was their April Fool's prank on Steve, I believe, where they all changed their background to match his. Thanks for everything. And the PhD is supposed to be a time, or is frequently a time of exploration. Usually that's scientific exploration, but sometimes it's just exploration. And so I want to thank all my adventure buddies, Jim, Ellen, Michael, Nike Massimo, and Sebastian, and a number of other people that the list is too long to really go through. And special thanks to Sebastian for now staying up with us until 1 a.m. I hope you're still awake. Thanks to my family, who've always been very supportive, sometimes maybe more supportive than was good for me, but thanks for everything. And also thanks to Nike, who has been my #1 adventure buddy and has even managed to bear with me through quarantine in a one-room studio with defense preparations under full steam without anything crazy going down. So thanks so much. So thank you to everyone for bearing with me. Sorry that I missed most of the people that need and deserve an acknowledgement, but we don't have all day. So thank you very much, and I'd be happy to take any questions. I think the way that we're going to do this, Allison, is this correct? There's a function to raise hands on Skype.
Yes, on Zoom, you should be able to click on a little blue raise hand button, and then Cole can call on you. So this is the time when we take questions from the audience, and I'm sure Cole would love to hear your questions.
And maybe if you can't find the raise hand button, you can just mark something in the chat. I see a question from Laura.
Yeah, hey, I guess I'll turn on my video. Great presentation, Cole. I had a quick question about something I think you went over quickly early in the talk with the the underarm support exoskeletons. You said that you wanted a parabolic trend in that, and I was wondering why is that true? Like, what is it about like the arm? Is it the geometry of the arm, or what was it about the arm that you needed that trend in your forces?
Right. So if you think about the arm as essentially a pendulum on a pen joint, which of course there's some barriers here with the hitting the torso, but if you think of it as a pendulum, if you have the arm straight down, you're at a singularity where gravity is pulling the arm straight down. You don't need any torque to support the arm. As you go out, that center of mass of the arm moves out, and you need more torque to support the arm, which varies as a sinusoidal function of that angle. And so that's the function that we were trying to support. Now, I do note that that kind of ignores the problem of the elbow. The good thing, relatively good thing, is that one, the elbow, or the center of mass of the forearm, is actually pretty close to the elbow. And so it doesn't change too much as you flex and extend the elbow. And so it is close to sinusoidal. The other point is that frequently it's not necessary to provide all the support. to fully do the task in order to be helpful. Sometimes you can just do some of the support and there's a big benefit. So that's what we were targeting here.
Great, thank you.
Okay, and I see a raised hand from Nathaniel.
Yeah, hey Cole. Yeah, great defense. On the running section at the end, I've noticed this a lot in my years of running with different coaches, how our feet can have different lateral movement depending on like how we plant them coming out a lot, or like how our feet are angled when we take a step. And I'm wondering what kind of effect do you think your device might have on this phenomena?
Right, so the ideal form of our device, I think, attaches directly to the ankle kind of in the middle of the leg so that it doesn't apply any sort of rotational torque around the leg. Unfortunately, the real world is not the ideal world. And so we did attach the shoelaces some distance in front of the ankle, and so that there is an internal rotation force, torque, applied to the leg. And so people do tend to kind of, it does tend to pull the foot inwards a little bit, and that may increase activation of some muscles in the calf that counter that rotation, such as the peroneus longus. But yeah, that is, so these are unwanted side effects of the real world implementation of our device. But the metabolic benefits that we see occur regardless of that effect.
Cool, thanks.
Thanks. Sophia. Sophia said, what do you think is the main differences? The main differences are between the ceiling mounted device and your device. And can I speak to body mounted forces? So I don't think I have a diagram. Maybe I do. This is an interesting question. I think that one of the main differences, is that with our wearable, oh yeah, here it is. Sorry, I have to share screen again. Nope, doesn't work. So one of the main differences is that our support, by the way that it's attached at the hip and under the arm, it produces a little bit of it produces a tensile force on the muscle tissue in the shoulder. Whereas the ceiling mounted device is angled slightly inwards. So there's a slight compressive force on the tissue. And this is kind of a big deal in stroke survivors because atrophy and other things that go on in a stroke, after a stroke, can cause a degradation of the tissues in the shoulder, which help hold it together. So it's not like in a robot where we have things just screwed together. The passive tissue is actually important to holding the arm together. And it may be that by pushing the arm out of, away from the shoulder, we're requiring extra work from that muscle tissue of the shoulder, which in turn makes the task harder, which decreases our results relative to the ceiling device, where it's actually helping to hold the shoulder together by applying a small compressive force. And that may have a better effect in terms of, it may make the task more easier because you don't have to worry about holding the shoulder together at the same time. So I think that that's one explanation for what's going on there. I've got another question. What's the effect of elasticity of extensor on the economy of running? So I think that this question is this question about the stiffness of the rubber band that we attach to the runners and what the relationship between the stiffness of that rubber band is with economy of running?
Yeah, I mean the stiffness of the Exotendon.
Right. So we experimented with different stiffnesses of the rubber band And it's not totally clear what the relationship is. So it may be that we ended up doing a whole optimization where we tried different lengths and stiffnesses of the rubber band. And none of the combinations that we came up with really performed much better than the one that we kind of defaulted to. And so it's a little bit unclear. It's difficult to get at the answer here because there's definitely effects of learning, which may be a major barrier to making these measurements in an efficient way. And it may also just be that it's not super sensitive to stiffness, but we don't really know what that relationship is without a lot more experimentation. So it could be possible that every individual needs a different stiffness and every running speed needs a different stiffness, but we don't quite know that relationship yet. But we do know that the device that we made and tested worked in all of our participants.
Okay, thank you.
Aha, Sebastian. Sebastian still is awake. Well done. Besides running, do you think rubber bands could aid other processes in humans? So I think Sebastian is referring here to, he really wanted to make a surfing rubber band that would help you to paddle out. And I certainly think that probably in that case, a better solution would be to just use the rubber band to power a little propeller. We have considered other tasks such as cycling, and we've played a little bit with the idea of swimming, but no one has really been brave enough to embark on those experiments. And with cycling, we've decided that the crankshaft couples the body together in a way that there is no real negative work done by the legs, and so it's not beneficial there. So there may exist some other processes in which rubber band can be useful, but it's complicated and requires a lot of experimentation. So Margaret Code's mother asks, why wouldn't the exotendon work for walking? And the answer there, we think, is that for those of us in kind of an engineering bent, I talked a little bit about the pendulum that oscillates at a natural frequency. As it turns out, the natural frequency of walking may be, or the natural frequency of the leg swinging back and forth may be very similar to the frequency that we employ when we're walking. Whereas running, we're trying to drive that leg at a higher frequency. When we add the spring into the system, we increase the natural frequency of the system, which is why we get a benefit in running. But that might actually make it harder to walk because now we have to fight against, like, rather than using energy to speed up the pendulum, we have to use it to slow it down. So Mimi asked, were all the participants to the rubber band experiments accustomed to running, or did you test it with naive runners too? So this is another very good question. At first, we were finding that there are some difficulties in which some of our more experienced runners were showing smaller or less of an effect. And so we were actively kind of looking for people that were very healthy and athletic, but maybe running wasn't their primary exercise. And so I think probably there's an effect here of you have to learn to run with the rubber band, and someone that's very used to running takes a lot of extra convincing to change what they do in order to suit the rubber band. And so they just maybe require a ton of extra training. So Allison mentioned that I do some amount of running. And in my early experiments with the device, I ran for a couple of weeks and tried the rubber band and didn't see any real effect. But then we took 2 months in which I would run 5K basically every day with the rubber band. And at the end of that, did see some effect. So there may be a substantial training phase to running with the rubber band that's more difficult to do with experienced runners than with naive runners.
Terrific. Fantastic set of questions. Unless there's anyone else who's really hoping to get something out, I think maybe we can unmute and applause Cole for a little bit. Applause Cole. Awesome. Thank you, Cole. Is there any other announcement you want to make before we go to the closed session?
We will be having a little bit of a happy hour later today. I have a Zoom link set up for that, but I haven't emailed it around yet. So maybe I'll follow up with that link in a minute.
Okay. Great. Thank you very much, Cole, and thank all of you. I thank all of you for coming. I really appreciate everyone coming out to support Cole. And so we will leave this meeting now, and those of us who are involved in the private questioning section part of the defense will go back into that other Zoom link. Okay, everyone have a great day.
Thanks.
Thank you.
That's all for now.